Hello and welcome back to Calculus 2, section 9.4, working with Taylor series. What can we do with Taylor series? We can calculate the value of the function, we can figure out the limit, and we can work with derivatives and integrals. You have to be very careful because Taylor series has to be centered around the region where you integrate. You know that your integral goes from 2 to 4. If you center it at 0, answer is garbage. So maybe you want to center it at 3 if the interval is 2 to 4 to get somewhat good approximation. Why is this so important? Well, today, unfortunately, is not as important for calculating, stuff that you need for engineering because we do have Mathematica and other software that can integrate and give you answers. This was used in good old times to find the answer without actually cranking crazy integrals. This does have, however, a much larger use later on in mathematics, in numerical methods, if you want to write the code, if you want to do asymptotic methods, so on. There's a lot of things that you can do with this section. Technically, we don't use it today as much as it was used in the past, but just because the fact that we have software today taking care of all of our integration, differentiation, and other needs, where we can focus more on the design and ideas rather than mathematical calculations. So what can you do? As I said, compute the value, compute the limit, differentiate, and integrate at the same time. They gave few examples of all of these. I want to talk about certain aspect of this stuff that you will actually need in differential equations and later on. But before we do that, I like to talk about favorite two problems. Why is the derivative of e to the x itself e to the x, and why is the integral, the derivative of sine x cosine x? And then you can use those to pretty much work anything else out. So I will start with the derivative of e to the x. Now, I'm not going to write derivative e to the x this way. I'm going to say what is the derivative of, and then write what the expansion for e to the x is. And if you take a look at the expansion, I got bored, so this is it. If I am to take the derivative of this, the derivative of 1 is 0, plus the derivative of x is 1. The derivative of x squared is 2x, and over 2, that dies. Plus 3x squared over 6, that dies. Plus 4x cubed over 24, and then that gives you 6. Plus x to the 5x to the 4th over 120, and that gives you 24. It's going to go forever, so I hope you see that we got the same back, right? Do you see what happened? So I wrote e to the x as a power series, and then I differentiated each term, and then the string that I got back is the same as the one I started with. So that's e to the x. That's cool. Want to do the same thing with the sine? So the next time Calc 1 student asks you why the derivative of sine is cosine, so who's the boss? All right. So what do I have here? I have the derivative of the sine, and that would be x minus x cubed over 3 factorial, which is 6, plus, you know what, let's go with the 3 factorial. And then x to the 5 over 5 factorial, and then minus x to the 7 over 7 factorial, plus x to the 9 over 9 factorial, minus dot dot dot. I got bored. So now as I'm taking the derivative of x is 1, minus, I have 3x squared over 3 times 2 times 1, right? So 3 dies. Plus 5x to the 4th over 5 times 4 factorial, so 5 dies. I peel off only 1. How about I leave this as a 2 factorial here? 7x to the 6 over 7 times 6 factorial, so 7 dies. Plus x to the 9x to the, so 9 times 8 factorial, 9 dies. Minus dot dot dot. So what you have here is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So you see how these are all even? And that's our cosine, right? Cosine x. And what was the derivative of cosine? Negative sign. Now look, if you are to take derivative of this, do you see how negative it starts, sequence with the negative? Yeah, right? So this would go x, 2x over 2, that will become an x, and that will be the first, but it will be negative x. So if you look at this and that, the derivative of that would be this sequence, except all the signs would be wrong. You factor out that minus, you fix all the signs, and it just becomes minus sign. All of mathematics always clicks together. You can go into one region of math and prove something different. Yes?
You were saying, like, this is more of a conceptual thing than just very specific. You're saying that, like, oh, if someone asks you what is the derivative of sine x equals cosine x, show them this. Like, is this why it equals that, or is this just the way through it equals?
Well,
like,
this is one of the proofs to show. You also can use the proof from Calc 1. There is a proof using a limit definition, right? Of sine of x plus age minus sine x divided by age, and then you have to use those limits, right? And limits are proved through L'Hopital rule. So there's a lot of different things that you could possibly do to get this thing working.
Is there going to be a third way to prove derivatives in Calc 3?
No, sorry. But now I'm interested in something else. I'm interested in taking the derivative of e to the x by actually taking the derivative of the summation that starts 0 goes to infinity of x to the n over n factorial. How does this work? How does this go back to e to the x once I take the derivative? So let's take a look. So I'm going to take the derivative here, and I'm going to get summation of n times x to the n minus 1 divided by n factorial. The counter shifts by 1 when you take derivatives on this. Now there is a whole proof for that, and if you're interested in it, you should try and prove it. It's not that bad, but you will use the limit definition, obviously. So now look at this. Now how's this equal to that to give me e to the x? So what have I done? technically nothing. I just wrote this as n x to the n minus 1, copy the constant. Nothing special. But now, if you are to compare, you see that this one starts at 0 and this one starts at 1. So you have to introduce that shifting the counter. You also see that there is n and there is n factorial, so at least one n can cancel. So if you are to peel off, so this is n goes from 1 to infinity, n x to the n minus 1 times n minus 1 factorial, right? Because if you peel the last term, the one before that is now in charge for the rest of the factorial. This dies. So just to make it clean, we have n equals 1 to infinity x to the n minus 1 over n minus 1 factorial. And now you say, okay, so I just need to shift this counter back to 0, and then hopefully that will fix the rest, and it does. So what you need to do here is to subtract 1 on both sides, and you will get n minus 1 equals to 0, and then you call this n minus 1 k. So technically you are using substitution k equals n minus 1. As soon as you do that, you're done. You can immediately see that it's over. Now I will challenge you obviously to go home and do the same thing for sine or cosine or whatever else you want. So it can be done easily. Now this shifting the counter is going to be important for your differential equations, because every time you take the derivative of a power series, the counter will shift by 1, and then you have to shift it back, readjust, keep going. So that takes care of this. Do you remember this from sometimes a while back? Yeah? Yeah. So those of you who come tomorrow morning to complex variables, you will see this done in a complex realm.
You say tomorrow morning?
Tomorrow night. Did I say morning?
Yeah.
Yeah, tomorrow morning, no. You're welcome. Yeah, 7:30. The last Wednesday, 7:30. Yeah, I had to skip 2 because of the schedule at that snow. I schedule things year advance, so then the schedule shifts and then mess occurs. So you remember this one? Remember how it was a whole page of work, and then there was that trick that you have to push to the other side, you create 2 and then divide by half, right? Remember that? Yeah, most likely not, right? Because why would you? It's insane. So 3 terms each. 1 plus x squared over 2, that's your e to the x. And then sine is x minus x cubed over 3 factorial, which is 6, plus x to the 5 over 120 dx. Foil, foil. Done. Right? How nice is that? Come on. Rejoice with me. This is awesome.
Yeah, but then you gotta foil it, and that's just so tedious.
Get out. You can do awesome stuff with this. You're turning all of your functions, all of your u subs and all of your, right, into nothing. Also, very important, so just now foil dx and equal to done, right? There we go. See, that's how you do these problems. All right. Now, remember how you can't even do this problem? You remember how you can't even integrate this? Yeah, you can't. You can't integrate this because you can't. However, if you're clever about it, you would immediately say, e to the x is 1 plus x squared over 2 plus x cubed over 6 plus whatever. And then you say, then e to the x squared must be 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6 plus going on forever. Because every x became x squared, so x squared to the first power is x squared. X squared squared is 2 times 2 is 4. X squared cubed is 2 times 3 is 6. Right? So now,
why wouldn't you square the bottom?
no, you're just replacing x with x squared. That's that property where you can nest functions. You remember when we had this and I said, do you think that this thing is useful at any time in life? That's exactly what I just did there. So I took the function that I can't integrate at all because there was no x for u sub. I took that function and what I did is I wrote it as a Taylor expansion and replaced this by, and I'm done. So now, what am I integrating? I'm integrating a joke. 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6. I'm going to cut it off there because we already seen that 4 terms are already good for your error, right? So you turn something you can't do into this joke over here, which is a polynomial, integration of a polynomial. Equals to easy. So this is the reason why on the first day when I taught about power series, I said it's not a power series, it's power series, you know? Because you can do stuff with this that is just amazing. You have to be, however, careful where you are centering your series. So if you are computing, and also this is not going to be exact. If you have to integrate from 100 to 200 and you center it at 150, obviously it's not going to work. All right. This works over small intervals that you can center in that region. So don't even try to integrate from 10 to 20 centering at 15 because the answer is going to be garbage. But if you have to integrate from 10 to 10.4 and you center it at 10.2, nice. Because these are approximations. They work over small distances. And again, we are honoring our ancestors because, face it, you plug this into your calculator, into your Mathematica app, Wolfram Alpha, right? And you get the answer instantaneously, so without doing it. And what are they going to do? Those rectangles. Well, I do 10,000, 100,000 rectangles in a split second and give you, whatever precision you need. You need more precision, they throw in more rectangles and you're good to go. So programming, right? So this is just like cool stuff to realize, right? It's in our math museum right now. And just because, computing power of, does anyone know how much memory original Space Shuttle computer had? How many computers? How many computers and what was the memory for each computer? The one that went to, the Apollo for the moon, first time. Yeah.
forget the number of computers, but it wasn't like the total, like, capacity was less than that of a modern iPhone.
Of course.
That's what my PSP.
Let me just. So that's
Yeah.
it for this section.
That's what my PSP.
We're done with this stuff. Anyone knows that? Bye, stream.